Alright, so today what we are going to do is, we are going to take the concept that we studied last time and we are going to basically apply it. Okay, so we are going to code the linear regression that we saw last time, and the idea is that, as I said earlier as well, it's not always sufficient to look at the mathematics, it's almost never sufficient to look at code. You have to look at both of them side by side. Okay, so last time, even after doing like hours of discussion, we arrived at a very simple gradient descent function, right? So it was theta is equal to theta minus alpha into derivative. Okay, remember? So that was the one equation, and what we did was we started with some random values of theta, and then we kept applying it for, let's say, 10 or 15 or 30 different steps, or let's say we kept applying it until we got to a sufficiently small loss, right, or sufficiently small derivative. So that's the essential idea. Now what we're going to do is we are going to write code for this same idea, and there are different ways of doing this. One is to write the whole code yourself using like pure Python or any language that you're interested in. So that has its own pros and cons. The pros are obviously that you are going to be doing everything yourself, so you're going to understand everything if you can manage to do it. Okay, so that's a good practice if you want to do it. The other option is to use a high level library such as scikit-learn. Okay, so scikit-learn we've already used before. The benefit of that is that you can definitely do it because it's just one line, and you give it the data and it computes the theta for you, and you're done. Okay, so that's another alternative. The negative of this is that you don't really understand anything because you don't see what's inside the black box. We did that earlier on with SVC, right? So it gave us the answer and we had no idea how it worked. The problem with writing everything yourself is that if you can manage to do it, then it's good practice, but the first step is quite difficult. Okay, so there is something somewhere in the middle, okay, and that is what we're going to go with. So the library that we're going to be using, we haven't seen this before in the course. I actually haven't taught this anywhere. I have quite a few different courses on machine learning, both in class and like paid courses, but I haven't taught this before. And the reason for this is it comes from the library which I mentioned to you earlier on in the first lecture, I think first or second lecture. It has its like history in Torch, right? So Torch was written in the Lua language. I worked with Torch and it was quite difficult to grasp the concepts of Torch. Okay, so it was very powerful. Torch was developed, by the way, by Facebook. So Facebook AI Research Lab, FAIR Lab. It's a huge player in the whole machine learning arena. They do a lot of stuff, and Torch was developed by them, but unfortunately it was in Lua language, and because of that there was a little bit of barrier, plus the design of Torch had some problems. It was difficult to get started with it. As a starting first step, it was not recommended, Torch. So the alternative for that was TensorFlow and Theano. So for a long while I worked with TensorFlow and Theano. TensorFlow actually came out while I was teaching in class, and the day TensorFlow was released, in the next class we actually discussed how TensorFlow worked. So it came out while I was working with this. So TensorFlow was also quite difficult to work with, just doing linear regression that we've done in class, and you can see it's just one equation. It's slightly difficult to work with. So people realize that TensorFlow is difficult, but people also realize the strength of TensorFlow. So there was this one guy called Francois something, it's a French name, I don't know. So he wrote the Keras library, which again I've given you a hint of earlier on. So he wrote the Keras library, and as soon as Keras was released, everybody just jumped ship from every place to Keras, because Keras was extremely easy to work with, extremely well written, very easy to get started with. You could write very large softwares using Keras. So everybody kind of moved to Keras. Okay, I also moved to Keras, and it was easy to just explain things. So for a long while, for at least like 3 or 4 years, Keras has been the undisputed leader. TensorFlow and Keras, the combination has been the, so TensorFlow is the low level library which is difficult to work with but very powerful. It's from Google. So Keras was written by Francois, who was working for Google, but Keras was not like for Google, it was his own pet project, and then Google basically incorporated Keras into TensorFlow because it was so popular that it was like overtaking the whole of Google's like efforts, right? So they just said, just put it in here, okay, and it was done. So everybody was using Keras. I was also using Keras. When so for a few semesters, I haven't actually taught machine learning formally. So I've been working with Keras and my own code and everything. So there is a point to this whole story, right? So just bear with me. So I was working with Keras and TensorFlow and everything, and I kept hearing about this port of Torch to Python. So Torch was in Lua, and people did not like Torch because they had to learn the different language. So there was an open source effort to convert the whole library of Torch into Python, right? So that gave rise to Pytorch. So Pytorch is essentially all the best practices of Torch, which was very powerful. It was before TensorFlow, by the way, Torch. So really powerful library, but in a language which people are more familiar with. Okay, so that is what Pytorch is essentially. So I kept hearing about Pytorch, and I never actually got around to it because I already had my own code base and I had like different models and everything was already prepared. I would just plug them in and make my research work. So I wasn't really interested in Pytorch. But when I was preparing for this class, I realized that Pytorch has now gained sufficient traction in the community that people are actually discussing, should we do Keras or Pytorch? At one point in time, I told you that it wasn't even a discussion. Like Keras was the obvious answer. But now there is a discussion. And I personally believe that in the future, because of some of the limitations of TensorFlow, people are going to move towards Pytorch. Okay, so that is why I wanted to do at least one introduction of Pytorch with you in class. Okay, so that's one reason I'm doing Pytorch. You need to know Pytorch. Going on in the future, even though a lot of the code that you will find online is going to be on Keras, right? Now, today, but in the future, because you'll be graduating like at least a year from now, right? So a year or 2 years or 1.5 years. So at that time, I think Pytorch is going to be very, very popular, and it would be something that if you don't know, then it's going to be like a deal breaker in most cases. Okay. So Pytorch, number one, in itself is a goal. Okay. It's something that you should know in itself, right? So you need to know Pytorch. Okay. You also need to know Keras, but Keras is easy. Like I said, I can do that after we do like detailed models. We can do Keras in one lesson as well. Pytorch requires a little bit of understanding because it gives you a little bit more power. So if it gives you more power, it also gives you the power to shoot yourself in the foot, right? So it's a common, I won't say proverb, but it's kind of like a saying that the difference between a revolver and a modern pistol is the modern pistol has a safety. So if you want to shoot something quickly, you have to take off the safety and then you shoot somebody or something. Okay. So a revolver does not have a safety. You can just, right? I didn't intend to do that. So, right? But it's also very possible to shoot yourself in the foot with a revolver, because if it's in the holster and you do something stupid, so it's going to shoot you in the foot, right? So Pytorch is something like that. So it gives you a lot more power, but because it has more power, it's going to require a little bit of more understanding. But that con is kind of like a pro for us. That's an advantage for us because we want to understand it. We don't just want to use the machine learning library. We want to understand how to do it, and we've already done the math. Okay. So now in this code, you are actually going to see the math being visible, right? Later on when we do Keras, you will see that in Keras, the math is not visible. Here, the math is actually visible. Okay. So we're going to look at the code. We're going to obviously look at what Pytorch is and how it works. But a secondary objective is to make sure that you understand that each line of code comes from the model. So there is an equivalence in the model that we did last time and the lesson before that. An equation is going to actually be visible over here. Okay. So all that discussion should become clear over here. So both of these goals are important in themselves. You have to be able to run it and you have to be able to understand the code. Okay. So we're going to look at this in detail. So to get started, you can go to pytorch.org. You can search for Pytorch and you'll get to their official website. So it has like a lot of stuff over here. The way you install it on your local machine is that you go to Pytorch build. You you select which one you want, either stable build or the preview, which is not that stable. You select your operating system. So if you're on Windows, you would click on Windows. Package, if you're using Anaconda. So those of you who are familiar with Python and Anaconda, if you're using that, you can use this, libtorch, whatever. You can select, do you want to do Python or Java, C++? You can select your platform, which is kind of like, do you have a GPU or not? But this is not all that important. I'll tell you why in just a minute. But you select basically the configurations that you want, right? And it's going to give you a command over here, which you can run on your terminal, and Pytorch will be installed. Okay, you can do that. And if you're working with machine learning on a regular basis, I would recommend setting it up on your machine. But because we are doing a demo over here and we want to just get started, we are going to start with Google Colab. Okay, so I believe we did discuss Google Colab earlier on. Okay, so you just go to Google Colab, create a new Colab environment or document, and Pytorch is by default installed. Okay, so Pytorch is just installed. You can start using it. Okay, all right. So I'm going to do it like this. Okay, so I created a new file over here. I'll share the file with you, but again, I recommend that you at least type the code once yourself, especially those of you who are going to be working with a senior project or like a semester project on this particular thing on Pytorch. I highly recommend that you run at least this thing once, because it's not that complicated. It will help you really understand not just Pytorch, it's also going to help you understand the maths. Okay, so these two are going to complement each other. Maths is going to help you learn what the model is doing, and this model programming is going to help you understand the mathematics really well. Okay, all right. So we start over here, and we are going to import some libraries. So Torch, obviously. So even though the library is called Pytorch, they use the name Torch because they're trying to use the same conventions that were in Lua Torch. Okay, so they are trying to keep the same naming because there is a huge community out there who knew Torch, so they don't want to mess things up for them. Okay, so the library's name in Python is Torch, even though the library's official name is Pytorch. Okay, you import NumPy. So NumPy is, again, maybe I discussed this earlier on, but I'm going to go through every line in today's lesson so that we have the completeness over here. NumPy is a numeric computing library for Python. So num is for numeric, right? So numeric computing, such as you can create arrays which are very high performant. You can multiply arrays with each other, like vectors, vector to vector multiplication. You have very fast matrix to vector multiplication. You have a lot of different highly optimized functions which come in NumPy. Okay, so NumPy has been around since before machine learning took off. It's a very, very stable, very, very useful library. Okay, so NumPy in itself is a goal if you're going to stay in this domain. We have matplotlib.pyplot. So this is the library which is used for drawing plots, and we're going to be drawing some plots over here. So the losses we are going to be plotting over here. Generally, it's recommended that you import matplotlib.pyplot. As you can see, it's a horrible name. Right, so matplotlib.pyplot, it's a horrible name, so you say as PLT. So what that means is this whole thing is going to be treated as just PLT. Okay, so when you write PLT dot, it's going to mean matplotlib.pyplot dot. Okay, so it's an alias, a shortcut. So this is there. Seaborn, I don't know why it's here, but Seaborn is a library, plotting library written on top of matplotlib, but matplotlib's plots by default look quite ugly. Seaborn has very nice looking plots. So it's out of habit, I just import it, even though it's not needed here. So in order to use Seaborn, all you have to do is just import Seaborn, and all your plots are going to look nicer. Okay, so if you're going to again do this thing on a professional level, you need to know these very minor things, because if your plots look ugly and you're going to present them to the lay people, like the people who are not technical, if your plots look ugly, it casts a negative shadow on you, right? Your documents, your plots, your code, everything should look neat. Okay, if it doesn't look neat, it casts a negative shadow on you. Okay, so anyway, Seaborn is a good library to work with. Okay, so you hold shift, hit enter, and it's going to run it for you after allocating the space. So it's connecting, allocating, blah blah blah. What we're going to do now is we are first going to create a function. Okay, so the function is going to be our ground truth. Okay, so we're going to have x-axis, y-axis. We're going to have a line. Okay, this line is going to be our ground truth. Okay, so look at this over here, the function -5 into x. So what this is saying is it's a function. The function's name is func. Okay, and this function multiplies -5 with the single input that is given to it. Even if you've worked with Python before, this syntax you may not have seen. Right, this is a different function, different syntax. But what it's saying is you're going to give it an x, and it's going to multiply that with -5, and give you the answer. So if you give it 10, it's going to return minus 50. Okay, clear to everybody? All right. This x is a torch.aRange function. Okay, so what does that mean? aRange is, I don't know what a stands for, but range is essentially you go from this point to this point, right? And you go from -5 to 5 and you pick a data point at 0.2 interval. Okay, so it's a lot easier to just explain it by
the space.
Yes. So you go from -5 to +5 and the jump that you take is 0.2. So you go from -5, -4.8, -4.6. So these are the values that you are going to get. So you're going to essentially get an array out, right? So the x-axis, this essentially we are creating the x-axis. So x-axis goes from -5 to +5 and the data points are 0.2 units apart. Okay, so let me just output this and then it's going to make more sense. So -4.8, -4.6, -4.4 and so on all the way up to 4.8. Okay, so -5 to 5 with a jump of 0.2. So this is your x-axis. Why do we have this? Because we are going to take this and we are going to feed it to the function func and it's going to return us the same number of y values. So now we have the x and y's. So x is our inputs, y is our outputs. So this is the ground truth. Is this clear to everybody? Okay, so this view -1 is just you're creating a window, it's not important. Okay, all right. So let's go ahead and plot this. Again, the exact definition of each function is not important. I'll explain what it does and then you can practice with it and you're going to understand it more. Okay, so what we're saying is plot x.numpy. So x is a torch array, right? So see, we created it using torch's function. So the way torch internally saves its arrays and the way numpy saves its arrays internally are slightly different, right? The internal structures are different, but we already have libraries which can work with numpy. Okay, matplotlib can take numpy values and plot them for you. So what you do is you take the Pytorch array and you convert it to numpy using a built-in function in Torch, right? So Torch people knew when they were writing Torch, they knew that everybody in Python knows numpy. So they had to play well with numpy. So they wrote a function .numpy which you can call to get numpy arrays back. Okay, this is a very common theme in machine learning and data science. You have 1,000 different libraries. And if a library does not work well with other libraries, it's not going to take off because people already know the 1,000 libraries. So if you create a new library and it doesn't work with 5 of the most popular ones, then your library is not going to be adopted by people. Okay. So all you have to understand for this is it's going to convert the x, which is a torch array, into a numpy array. Why? Because matplotlib, which is PLT, can plot numpy arrays, not torch arrays. Okay. Is this clear?
Can you show us how it looks different?
So if you try to print it, it's going to look exactly the same. So numpy array looks exactly the same like this. But internally, the way it's stored in RAM, it's a different structure. Okay. And the reason for that is numpy people optimized it using some other logic and torch people optimized it using some other logic. I can give you an example. You can have an array in an array, right? Or you can have it in a linked list. Have you worked with linked lists?
Yeah.
Right, so everybody worked with linked lists,
Yes.
right? So different internal structures, right? So it depends on what they're doing. So if you print them out, they're going to look the same. 1, 2, 3, 4, 5. The numpy array looks exactly like this, except over here it's going to say ND array instead of tensor. Okay, is this clear? Okay. So the point is, if you don't convert it into numpy, matplotlib will not be able to work with it. Okay. You're also taking func.numpy. So func is our ground truth over here. So func is -5 into x, which means take each element and multiply it with -5 and create a new array. Okay, so when we output this, it's going to make more sense. This R means the line which you plot over here should be red and the label should be func. Okay, label is anything that you want. The x label, the label on the x-axis should be x and the label on the y-axis should be y, and you also need a legend. So you'll see what a legend is in just a minute, and you also want the grid with the yellow color. Okay, and then you're saying just show me this plot. Okay, let me run this and then it's going to make sense. So the line is red, this thing over here. Okay, x goes from -5 to +5. Okay, and the relationship between y and this is, if this is -4 into -5 is going to be +20. Okay, so that is how we get this line. Is this clear to everybody? Okay. You can convert this into, let's not do that. Okay. So this thing over here is the legend. Okay. So if you have multiple plots, you can have different entries in the legend over here. Okay. This grid is yellow. Why is this yellow? Let's make this gray, not green. Ugh. So, okay, looks better. Okay. So I don't know why I put yellow there. So the lines are changed. It's not important. The grid lines are changed. No. Okay. Whenever I'm doing anything like remotely related to plotting or anything, I spend like half the time doing the plots and the other half the time making the plots look nicer. So I waste a lot of time. So anyway, coming back to the point. Okay. So we have this is the ground truth. Remember, this is the ground truth. Okay. This is the relationship between x and y. The relationship that we are trying to get. Okay. Which is to say, what is the number? So this 5 minus 5, what is the number which is multiplied to get to x to get y? Which number is multiplied to x to get y? So when we create our hypothesis, we want in our hypothesis function, theta 1 should be minus 5. Okay? We put minus 5 over here so that when at the end we get the result, we can compare. So we start with the ground truth that we created ourselves. Why? So that we can be sure what the answer is. Okay. So now we are not going to show this minus 5 to the machine, and we want the machine to learn the minus 5 looking at the data. Is this clear? Okay. So we created the ground truth ourselves. When you're working with real life data, you don't know what the ground truth is. That is a problem in itself. Okay. So for example, if you're trying to predict the weather using all the different factors, you don't really know what the internal relationship is. Okay, but here we want to keep it simple so that we can verify that our model is actually working properly. Is this clear? Okay, so now what we're going to do is we are going to generate data from this ground truth. Notice the difference between these two. One is what is going on in the real world. In the real world, the relationship between x and y in an ideal world in which nothing goes wrong, no sensor has any error, anything wrong doesn't happen. Okay, then the relationship between y and x is minus 5. Minus 5 into x is y. This is the relationship. But when we gather data, when we try to install sensors and measure the temperature and everything, we have some errors, minor errors in our sensors, in our data collection and all of those things. Okay. So now we are going to introduce those errors in this data. Okay. So let me write the code. Again, when I say this, it's not going to make sense. When I write the code, it's not going to make sense. When I write the code and then come back to this, then it's going to make sense. Okay, so these three things go together. Your maths, your code, and your visualization. If you have these three things, then you're going to understand the concept well. Okay, so I'm going to show you the code now. So what is y? Remember the first thing we called func, not y. Even though we plotted it on the y-axis, we didn't call it y. Why? Because why? Because the y, the letter y, is our output variable, the thing that we measure. And we cannot measure 100% precisely, ever. In the real world, you cannot have an infinite precision. You're going to have some sort of an error. Okay? So we are introducing that error over here. How? We are saying take the value of the ideal values and then add to it 1.7 times this some random number. Okay? So let me explain what this is first. Do you understand what we're doing? We are taking the absolute perfect ideal values and we are going to add some noise to each of the data points. Why? Because we are going to simulate that when I measured the first data point, I got a little bit of error. When I measured the second point, I got a different error. So all the different errors. Okay. So I'll show this to you and then it's going to make more sense. But see over here, what we're saying is create an array. Torch has a function called rand_n, which says create an array of random numbers, but how big should this array be? That is x.size. Okay. So for this, what you do is you come over here and you say x.size. Do you see what I'm doing? I'm printing out this thing even though it's not part of the code. I'm going to print it out so that it gives me a number so that I can understand what is being passed to this function. Okay. So if you say x.size, it says the size is 50,1. It has a total of 2 dimensions. Okay. The size of the first dimension is 50 and the size of the second dimension is 1, which means it's a vector. Okay, a row vector. Okay, is this clear? So this I'm giving to this rand n. What this rand n is going to do is it's going to create an array of the same size, but this time random numbers. Okay, and rand n generates a random number between 0 and 1. Okay, what we do is we multiply that 1.7 by 1.7 so that the error is slightly larger. If you multiply any number with 1.7, it's going to increase in size, right? Everybody agree? Okay, so this 1.7 was not necessary. I'm just trying to increase the error size. So what you can do is now you can create a ground truth using func. You can also introduce errors and change the size of the error. How much error do you expect when you're doing data collection? At the moment, I expect 1.7 units of errors on average. Okay, so let's run this and you are going to get a y. Now we are going to do the plot again, but we're going to x dot numpy on the x-axis, y dot numpy on the y-axis, and we're going to make them blue. Okay, you'll see what the plus means in just a minute. We are also going to plot func dot numpy as we did before, and we are going to still make that red. Is this clear? So we are plotting both things. Okay, so now look at this. Hopefully now it's going to make sense. The ground truth was there. That is what we want to learn. But the machine is never going to see this line. The solid line is never going to be seen by the machine. The machine is only going to look at the blue points. And if you only look at the blue points, now you can imagine that there is a possibility of errors. Because you can never hit all the blue points with a straight line.
So we just move backwards?
Yes, so essentially you're going to now get rid of this red line. The thing that you're going to show to the machine is not this, sorry. The data that is going to be fed to the machine is not func, but y, this thing over here. And now you can see that, yes, it kind of looks like an inverse relationship, but the straight line can be, it can have some wiggle. Okay, it can move around. Okay, it's not 100% correct. So that's the problem when you're doing machine learning in practice in the real world. And even though this is not real world data, we still want to work with some error so that later on when we do move on to real world, in the real world you're going to get this. For example, the housing prices that we did, it was the same idea. Some data points are, see, for example, for, let's say for this point over here, right? This point is very low and this point is very high, even though they're very close together, right? So these two are very close together and this one for some reason is here. Maybe the sensor which collected this data point had some dust on it. Okay, so you got this error. Everybody understand? You were measuring temperatures and you got this data point which is like an outlier or something. Everybody understand? So the machine is going to see this. It's never going to see that -5. All it's going to see is x and y. Okay, so let's output x. So it's going to see x, these values, and y's, which are these values. Okay, so remember the table that we had for the data set? Number of rooms, area and price. So now we have x and y. It doesn't matter what the actual features are. It's just x and y. Okay, is this clear? This is what the machine is going to see. The machine is never going to see the -5. The machine is going to arrive at the -5 itself. Is this clear? Okay. So now what we're going to do is we are going to define some of the pieces which are going to be needed for our Pytorch model. Up until this point, we were just preparing the data. We have the data. Now we are going to do actual machine learning. Okay. So here's what you need for the whole model. Number one, you need a loss function. Okay, let's start with that. So I'm going to go up and down over here. You need a loss function which is also called a criteria. So energy, loss, error, cost, criteria, all of these things. Okay, do you remember which loss function we used? Mean squared error, right? So we are going to calculate the mean squared error over here, except we're going to use the facilities provided by Torch. Okay, so we are going to take ypred. So this is a function criteria which takes two things: the predicted y's and the ground truth y's. Okay, it's going to take these two things. Okay, and it's going to subtract one from the other, then it's going to square it, which does the square, and then it's going to take the mean, except we don't take the mean by 1 over m. Right? Do you understand what I'm saying? In order to take the mean in our equation, in our mathematics, we had 1 over m. Okay, and we also had the summation. So summation and 1 over m combined gave rise to the mean, the average. You sum all the values and then you divide by the number of values. That is how you get the mean. Here we are not doing that ourselves because we have a function torch.mean over here. We could have run a loop over here and then divided by the number of values in y, but you don't do that. Can anybody recall why?
Because it's more optimal.
It's much more optimized. I told you, if you have a library which can do something for you, use the library, because torch people have spent ages optimizing the mean. If you give it a million by million thing, it's going to do it like that. If you write a million by million thing and loop over it yourself, it's going to take hours. So it's the difference between milliseconds and hours. Okay, just this one thing. You understand? Okay. So, but do you see the loss function here? The same loss function, the mean squared error that you saw in mathematics. Do you see it over here? If you don't, you should. If you don't, ask me that I don't see it, so that I can explain it more. This is the y pred minus y or y minus y pred. Doesn't make a difference because we're going to square it anyway. Okay, you can have them in the different order. And when you do the squaring, then you calculate torch.mean, and this y pred and y are both going to be vectors. So they are going to be subtracted element wise, squared element wise, and at the end torch is going to take the mean. So torch is going to do all of that for you. You write something which looks very close to what you had in mathematics. Is this clear? Notice y pred and y are, I'm telling you, they are both vectors, but there are no indices. You're saying y minus one vector minus the other vector. How is that going to happen? If we wrote the code ourselves, we would loop over the thing, right? Here you don't have to. Why? Because torch tensor minus torch tensor is predefined to have a very highly optimized subtraction, element wise subtraction. Is this clear? All right. All of this it's very like theoretical in nature. When you do it in practical, then you understand it well. When you do it yourself, okay. So I'm going to give you an assignment for this thing so that you can run it yourself as well as before. Okay. So this is our loss function or criteria function. Okay. Again, it's a different name for loss function. All right. So this is our loss. Okay. So what do you need? Again, let's go back. You need to start with some random values of theta. Okay, we'll see what theta is in just a minute. We haven't seen it at the moment. When you run it, you need to calculate the loss, okay, because you need to know what the loss is currently. You also need the derivative, okay. Why do you need the derivative? Because you want to put it in that gradient step, gradient descent step. Theta new is equal to theta old minus alpha of alpha into the derivative. Okay, is this clear to everybody? You need it for that. So in order to go forward, or your hypothesis, so the forward is your hypothesis function. It's going to become clear later on what we mean by forward. So what forward means is that you apply your hypothesis. Okay. So what is our hypothesis? We are going to have some x which is going to be given to us, and we are going to multiply it with some theta. So because we cannot write theta easily in programming, it's Latin or Greek or whatever, I don't know. So we use w in its place. Is this clear? I'll say this again. Your hypothesis function said theta 0 plus theta 1 into x. We ignore theta 0. We only have theta 1. So theta 1 into x. That is our hypothesis function. Instead of writing theta 1, we write w. Is this clear? So this is your hypothesis function. We call it the forward pass. Okay. It's going to become clear later on why we call it the forward pass. Is this clear? Okay. Good. So we are going to run this. This is our forward pass. This is going to calculate the loss for us based on the current values of w. You will notice we don't have w over here. For this function, we have one parameter x. It doesn't have a w. We're going to define w as a global variable later on. Is this clear? Okay. This is your loss function. You run this as well. This is just defining the functions at the moment. Okay. Then we are going to create a w, which is going to be a torch.tensor. Okay. And this is going to be just a value minus 10. So we are starting with a random guess of minus 10. Okay. What this is saying is, forget about this for a minute. What this is saying is, create a tensor, of size just 1, right? So it's still a tensor, but it has only one dimension, and the size of that one dimension is just 1. Is this clear? You would think that would be a scalar, but no. It's still a tensor for certain reasons, okay, programming reasons. You have to define it in terms of torch.tensor. You cannot say w is equal to minus 10, because then Pytorch will not be able to work with it. Okay, make sense? Okay, all right. So this is the starting value of minus n. If you want to start with a different value, you can let me know. We can change it. Okay, it's a random value.
Just one question. Let this function before.
Yes.
This is what does it calculate exactly?
So it's calculating. It's going to take two values. So let's say you have. I'll say the whole thing. It's okay. I'll say the whole thing. Maybe that answers your question well. So you are going to have some x's and some y's. Okay, you have that in the data set. You are going to apply your forward function on each x to get some predicted y's. So now you have predicted y's and ground truth y's. You take these two vectors, you give it to this function. It's going to do element wise subtraction. You get some values. It squares each of those values and then it takes the mean of the whole thing. Is this clear now?
Yeah.
Okay, good. So these two are vectors. That is the important bit over here. Okay. How do we know? In Python, you don't have a data type. So you just know, I just told you. Okay.
So the forward calculates the predicted wise?
Yes. Forward is essentially your hypothesis function. Okay. It's not 100% accurate, but for now, it's your hypothesis function. Okay. All right. So this over here, we are calculating a W. Okay. And this thing over here is why you don't need calculus. So all you have to do is, you have to tell Torch that this is a parameter of my model. Somewhere along the line, I'm going to need the derivative of my final function with respect to this W. Requires gradient. This grad is for gradient, not a graduate student. It's a gradient. What it's saying, require grad is equal to true, is saying that this W is a parameter. I'm going to require its gradient so that I can change it. Right? We wanted to change theta based on its gradient, right? So that is what we're telling Pytorch. And Pytorch is going to calculate the derivative for us automatically. We don't have to lift a finger. Is this clear? We give it the loss and it's going to calculate the derivative for us. Okay? So just to like finish this whole thing up, in the loss, in this loss over here, can you see W? You cannot see W, right? But is W there? Is the effect of W somehow going to be in this thing?
Yes.
How?
Why create?
Yes, right. So I'm going to say this. Even if you don't understand, I'm going to say this, but it's good that at least one or two people like understand this. Okay. So this y pred comes from the application of forward on all the x values, right? Where does this y pred come from? When you take this forward and you apply it on all the x's. So W is being multiplied with all the x's to give you y pred, and then this criteria takes this thing and then does the whole thing. Okay. So when you create the derivative of this criteria, you can take the derivative of criteria with respect to W. Why? Because in the whole definition, if you expand the whole definition of this criteria, it's going to have the W somewhere. Okay. Because you can replace this y pred with W into x. Everybody agree? Right? Why? Because how is y pred calculated? By multiplying W with x. So this is your function. Just think of this as your mathematical function. So you can create the derivative, you can calculate the derivative of this function with respect to W. Okay? Not with respect to x. When you do calculus, you typically calculate derivative with respect to x. Right? Why? Because you are changing the x. Here we cannot change the x. Why? Because it's in the data set. It's what we measured in the real world. We cannot change it. We can change the theta, which is the W here, which is a source of constant confusion because you have different terminologies for different areas, right? But I hope it's making sense. Okay. So what Torch is going to do is it's going to take this criteria, calculate the derivative for you for this function with respect to W automatically for you. Is this somewhat clear? We're going to go to the end and then we're going to come back over here. Okay. So let's run this as well. And it's going to give you the W, which.
So W is a hyperparameter?
W is the model parameter. It's theta. Hyperparameter we have like over here, right? This is the hyperparameter alpha. Step size is equal to 0.1. Okay, this is alpha. Let me write this. So this is alpha. We don't typically write alpha. In code we write step size. Sometimes we do write alpha. And there is a language called Julia which can actually allow you to write the alpha. Okay. Lossless. Here, whenever we create the loss, we change the theta and we create a new loss, we are going to save this, which has nothing to do with the algorithm, but we want to see how the loss changed over time. When the theta was minus 10, what was the loss? When I updated it, what was the loss then? How was the loss changing over time? I just want to see. That is why I have a list over here in which I am going to save the loss values after each iteration. After each time I change theta, I am going to save the loss value. Loss value, not loss value. Is this clear? And I want to do the whole iterations 20 times. I am going to fix the number of times I am doing it. Okay? There are certain reasons for that. I don't want to go until I get a derivative of 0. I want to go until 20 iterations are done. Is this clear? Okay. All right. So now we are going to loop. Okay. For I in range iter, so this means go from 0 to 19. 20 times we are going to run this whole loop. What are we going to do? We already have the x. It's a global variable defined at the top, right? We are going to create ypred by applying forward function. Okay. Please make sure that you follow this over here. We are going to calculate the loss using the criteria function. We are going to send it the ypred and the y, and it's going to calculate the loss for us. Okay. We are going to save the loss. So loss list dot append loss dot item. Okay. This item essentially means this loss is going to be a tensor from the Pytorch structure. Right. It's a Pytorch structure. Right. We want to convert this into a value, like a Python value, not a NumPy value, but a Python value. Okay. So for that we use the item. Right. I'll say this again. It's going to have some number. The loss is going to have some number, but the internal structure of that is related to Pytorch. We want to bring it out so that we can just use it using a normal Python thing. Okay, is this clear? And we are appending it to our loss list. So each time in each iteration, we are calculating the forward pass based on our current value of w. Right? I started with minus 10. I'm going to multiply minus 10 with all values of x. I'm going to get a list of predicted y's. I'm going to calculate the loss, which is going to be a single number, not a vector. Why? Because you take these two, you subtract, you get something, you take the squares of all of them, and then you calculate their mean. So the mean is going to be a scalar value, single value. Okay, so the loss is a single value over here. Then you write this function over here, loss dot backwards. So loss, remember, is this criteria over here, and we say loss dot backwards. So this one single line is going to do all the calculus that you want it to do. It's going to calculate the derivative of loss with respect to the variable that you marked as required grad is equal to true. Okay, I'll say this again. This dot backwards is going to calculate the derivative of this function with respect to all the variables which you marked as requires grad is equal to true. All the variables. Here there is just one w. But later on, we are going to see that we are going to have millions of different values. And we don't have to calculate the derivative of anything. All we have to do is just mark them. I need a derivative with respect to this, with respect to this, with respect to this, with respect to this. Okay? And then you go ahead and do the dot backwards, and it's going to calculate the derivatives like that. Okay? No calculation needed. Is this clear? Okay. How does it know? It knows because loss is a function. Okay, so it's a function, right, which has some multiplications and divisions and squares and means and averages and all of that, right? So the computer is dumb, but it's not that dumb. It can look at the operations which are being performed, and it can do the derivatives and apply the chain rule and do everything for us. Okay, so we no longer have to do it. You have to understand the essence of calculus. That is a separate thing, but you don't have to do the calculations by hand. Okay, so is this clear? So this is going to calculate the derivatives for you. It's not going to change w. It's going to calculate the derivative of loss with respect to w, okay, at point where w is equal to minus 10.0. If you're trying to calculate the numerical value of a derivative, you need to give it the point at which you want the derivative, right? So if you have a sine function, its derivative is going to be a formula, which is cos. If you don't remember, sine is minus cos or cos? I don't know. I don't care. Okay. So it's going to have a derivative. Okay. But it's going to change depending on where you calculate it. Okay. The derivative value is going to change even though the function remains the same. So what this is saying is it's calculating the loss of this function with respect to w at point w is equal to 10.0, which if you remember from your mathematics was the loss for the theta 1 that we picked. So if we picked theta 1 is equal to 4, we were interested in the derivative value at that point, which was what, minus 6 or something? Whatever the derivative was. Okay, it was, let's say, minus 6. Right? Now what we are going to do is, we are going to update W data by taking the previous value of W data. W dot data essentially means the value. Okay, these are different, dot item, dot numpy, dot data, all of these are there. We are going to multiply it with the step size, which is alpha, and multiply this with W dot grad dot data. W dot grad dot data essentially is going to be the gradient value. So this is W's value, and this is W dot grad is the gradient of W at that point. Okay, and as you can see, this is exactly the gradient descent step. Can you see it? Okay, so this thing over here is the alpha. Theta is equal to theta minus alpha into gradient. Okay, right, so this is theta is equal to theta old value minus alpha into gradient value. Okay, does it look like that? Right, so W dot grad has the derivative of loss with respect to W at this point. Okay, so it's the same thing that we saw in the mathematics, right? So what this is going to do is it's going to update W. Okay, and now you're going to do the same thing again. You're going to calculate the forward pass using this new W. You're going to calculate the loss for this new W. You are going to append the loss so that you can like look at it later on, and then you're going to calculate the derivative of the same loss with respect to W at this new point. Okay, and then you update W again, and you keep doing this until 20 times, exactly, right? So here we're doing it 20 times. There we were saying until the derivative gets close to 0. You can add that condition over here, but for now we are doing it 20 times. Okay, just one final thing. Once you are done with one iteration, you want to change the gradient. You basically want to zero it out, because with each iteration, what you're saying is the next time when you calculate the derivative, don't take this derivative into consideration. Okay, that's just how the mathematics works. So this thing is just going to be there. Okay, always. Whenever you start a new iteration, calculate the derivative again. It's Pytorch's requirement that you zero it out first. There are cases in which you don't zero it out. It can lead to different behaviors, and sometimes you want them, sometimes you don't. But when you're getting started, you want to zero out the gradients before the next iteration. Is this clear? Okay, and then we are simply outputting the values. For each iteration, we are outputting the value of loss and outputting the value of W. Okay, what is the current value of W and what loss is it leading to? Okay, and the gradients we are going to, we can also output the gradients. So let's say W dot grad dot item. So let's just first do it without this. Yes.
Wouldn't it be 0, the graph, if we output it now?
Let's see what the values are. I don't know. Okay, so let's output it. So this whole thing is inside the loop. Okay, so whole thing is inside the loop. We are outputting this over here. So let's run this, and we have an error. Where is the error? Okay, I did not run this. Okay, so iter, and now run this. Okay, right. So we started off with the W dot item with at the end of the first iteration. We started off with 1.0. 10.0, minus 10, right? After the first derivative was applied, it turned into minus 1.6. And for minus 1.6, the loss was 213. Okay. Then we updated it again. It went to minus 7.2. As you can see, it has overshot on the other side. Okay. The actual answer is minus 5. We know because it was at the top when we generated the data. The machine has never seen minus 5. Okay. So then it overshot on the other direction, minus 7.2, and there the loss was 96. And then it went on the other side, minus 3.4. So it's getting closer and closer, right? So it's going from here to there. This is the minimum. It started with minus 1.6. So let's say this is 0. This is minus 5. So this is minus 1.6. So it started from here, then went over there, then went over here. So it's getting closer. It's jumping around on either side. It's not going smoothly, but it is getting closer. So it's not diverging. Do you see? Because the loss is decreasing. If it was diverging, then the loss would have been increasing. Do you see? So it is converging, right? We know what the actual value of the ground truth is. What the actual value of W should be? -5, right? Because -5 is going to lead to that data, ideal situation, okay? But we don't look at this because in the real world, sometimes you don't know that. You look at the losses. You look at the losses, and if the losses are decreasing, it means you are converging. You're not diverging, because if it was diverging, remember, if we go further and further away from the minimum, the loss is going to increase. We're going to look at that situation over here as well. Okay. So see, eventually it settles down to 4.8, 5.0, 4.9, 5.0, 4.9, 4.99, 4.98. Right? It's pretty close. It's not 5, but it's pretty close. Okay. We could have this run for like 200 iterations, and then it would probably get to like very close to 5, but we say it's sufficient. Is this clear? Okay. One. With practice.
Where did you decide?
So over here. So iter is equal to 20 for I in range iter. So we are going from 0 to 19. So exactly 20 times.
But how do you know?
I don't know. I just picked this out of the blue.
I mean, in this case, you know that it's -5. So
Yes,
you know
yes,
what
yes.
it's done.
Yes. When in the real world, when you don't know what the actual value of theta is, right? You look at this and you keep seeing this and you say it's very close. It's 4.976, 4.970, 4.974. And if you run it for like 10 more iterations, so let's run it. Right? So let's run it for, let's say 30. Okay. So it's going to continue from that point onwards because W is currently -4.9. So it continues and it gets to -4.972798. Right? So it's not changing beyond like the 5th decimal point. And after a certain while, I'm going to say, just stop. You're not changing. Okay? You see? Let me plot this and your question will be answered even further. Okay? So remember, I had the loss lists. I'm going to now go ahead and plot them. Okay? So I'm going to plot the loss list. What is the loss list? With each iteration, I save the loss. So let's go. It's the same thing which I'm going to plot. So see, the loss started off with a very high value, and then it came down. And over here, now it's not changing. It's kind of like just staying there. So that is how you know when to stop. If the loss is simply not changing, and you've been going on for like 200 iterations, and the loss is not changing, it means it's not making any difference anymore. So just stop. Okay? Is this clear to everybody? That is what we taught for a long while, and then there was a research paper which came out, and they said if you like wait for 500 iterations, sometimes the loss does go down, and everybody was surprised, but it's not your concern at the moment. Okay, so in like professional industry cutting edge technology, some of these rules, kind of the guidance that I'm giving you, they break down. Okay, because it's an open area of research, everybody's working on it. Okay, anyway, so does that answer your question? How do I know? I look at the thing and I decide to just it's enough. Okay, all right. So let's go over here and now change our let's say. So let's reset the W. Okay, so let's reset the W to -10.0. Okay, I'm going to change the step size to, so step size is equal to, let's say 1.0. Okay, so step size is 1.0. So now let's run. Yes.
In the loop, yeah, if you can go to.
Yes. Yes.
This backward is a built-in function that calculates the gradient.
Yes. It calculates the gradient of this function with respect to all the variables in it that you marked as requires underscore grad is equal to true. Okay, which in this case is just W. At this point, current point of that variable. Okay, whatever the current point is, which is -10.0 when we start. Okay, that is important. All right, so we have this thing over here, and just before we finish, so you figured out that it has actually gotten very close to the actual ground truth. Why not exactly -5.0? Because there are some errors in the data that we collected. The more the errors, the harder time machine, this information is simply not there. Okay, so if you have a lot of errors, the machine can have different slopes which all match, which minimize the loss. Okay, and that is a separate problem that we'll come to later on. All right, so let's run this for step size equal to 1.0. Okay, so we run this for again 20 iterations, and now you see over here it started with the same 2 or 13 loss. Okay, it shot up to this thing. The loss has increased, and this has gone from 73 to minus 1240. See, it started off with a positive, and then it overshot minus 5 to very far away to minus 1240. Then it tried to came back, so it's going in the right direction, but 1937, I don't know, 19,000 something. Okay, then it tried to turn around and then overshoot and 30,000. So it's diverging. So this is the case of divergence. When you see this, that the loss is increasing, and see after a certain point it's just infinity. Okay, so the loss is infinity. That is a good indication that it is a diverging situation. And when you have diverging situation, what do? Decrease the step size. So
Can we see the graph?
yes, right. So you want to see the loss of this. So the loss looks like, so there is a little bit of a jump over here, but after that it just shoots up. And the reason that it looks like this is a huge number, right? So the plot, essentially this whole thing is, there are variations, but the graph is so squished that it looks flat. But you can see it goes like, okay, up to infinity. Is this clear? All right. So maybe if you want to see this, so let's run this for just 5 iterations, right? So let's reset the W and let's run this for just 5 iterations so that you can see the loss better. Still, even with this is really horrible. So let's run it for like, I don't know, 3. Keep doing this, it's going to take you a lot of while, but it's shooting up. Okay. All right. So what else? So let's go ahead and change this to 0.001. Okay, so let's see what happens when we have the step size very small. Okay, so we started off with the kind of optimum so that you know what the answer is, right? But if we start with 0.01 and we need to reset the W, so let's reset the W over here. Oh, right. Thank you.
Now we set the W.
Oh, no, you set the W again. Right. All right. So you already know what I'm doing, sir. So see, it started with 213. It was at minus 9.9. It took the step, but it's small, but it's in the right direction, and it keeps going. And when we get to our 20th iteration, we see that there is like a big change happening over here. 8.7, 8.6, 8.6, 8.5. It's still changing. Right? So this is where you figure out that yes, it is changing. I have 2 options. Number 1, increase the step size. Number 2, increase the number of iterations. Okay, I can try both depending on what I'm trying to, like what kind of data I have, what other information I have about this. Okay, is this clear? Any questions about this? So here you can, let's say, you can go ahead and say let's increase this to 100 iterations. I don't want to reset the W because, all right, let's reset the W first. I don't care. All right, and let's do the plot. And as you can see, the loss is consistently decreasing. So even after 200 iterations, I can see that it's still decreasing. So I should probably change it to like 300, right? And the good thing about Pytorch is you don't have to reset the W. You have the W over here, which is achieving this. You can simply go ahead and run these iterations like 200 more times. And now it's kind of stable. Okay, now it doesn't look like it's going down anymore. Okay,
so increase and decrease
right. So it depends on your learning parameter. Okay, so this thing over here, it's minus 5.14. Okay, so first it converged to slightly below 5, and now it's slightly above 5. Right, so the other way around. First it was slightly above minus 5.0. Now it's slightly below 5.0, which is in the negative, this thing over here. Right, so you see this thing over here that looking at the loss, even though the machine doesn't need the loss. See over here, we calculated the loss, right? We calculated the loss over here, but we only needed that for the derivative. The loss is for us humans, so that we can look at the plot and make decisions, right? So let's go over here and change this once more, and maybe we can try 0.2 and see what that gets us, right? So let's change this to 20. So what is this? So 0.2 again does not work. Okay, it's diverging. Everybody can see it's diverging? Okay. No? So now can you see it's diverging? Okay. That is why we do plots. Alright, so minus 0.2 does not work. How about 0.15? That still doesn't work. So maybe 0.1 really was best. Right, so 0.11 gets to the what, I didn't reset it? Yep. So where is it? Okay, so it gets to minus 5 pretty quickly, right? So like over here, right? But because it's jumping around, right? Can you see? Right, so you have to experiment with these values. So you see over here minus 4.49, minus 5.37. It overshoots over there, and then it's taking such large steps that it cannot get to that small minor thing. Okay, so generally what you would do in situations like this is start off with a large enough step size. Okay, as long as you don't have divergence. Okay, if it is converging, you start off with a large step size and slowly reduce the step size. So once we are over here where it's jumping around on the second or the first decimal place, okay, now we go ahead and reduce our step size to 0.001 or 0.001. So very small, but now we don't reset the W and we go ahead and run this. So now it started off with that and now it has gone down to 5.06. Okay, so we started off with a large enough step size so that we can quickly get to the minimum, but if you keep that large step size, it's going to keep jumping around the minimum because it's taking a step and it's missing it. It turns around, takes a step and misses it. Why? Because the step size is too large. Okay, so then you try to reduce your step size and then you can get to this. So after this, if you want to get even more accurate, let's say you're like writing this for a nuclear reactor, you want a lot of precision, so you're going to run this again. And now you can see that it has converged all the way up to at least the fourth decimal place. Okay, so 5.555555549. So like fourth, fifth decimal place, it's very accurate now. Is this clear? Okay. So when you reset the W, it goes back to 10.0 and you start from the first iteration. When you don't, it just continues. So at the moment, right now, the value of W is minus 5.069 blah 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 blah, this thing over here. If you don't reset it, it's going to, if you start learning it, it's going to take this as the starting point.
It was minus 5.14.
Exactly. So it started with minus 5.14, which was already pretty close to the correct answer. But we said fine tune it, I mean go a little. So you started off at and now you're here, you're oscillating here. So you decrease the step size and now you can go here. And you decrease the step size further and you can go to the absolute minimum. Okay, if you reset the W, you go all the way back to minus 10.0 and you start from there. Does everybody know what this is? Okay. You can. So when you're running experiments, we break them down into different cells so that I can decide if I want to reset it. But when you have this whole thing in Python code, it's going to be like one big thing and it's going to run the whole thing at once. That is why we do Jupyter instead of Python's scripts, because that is going to run the whole thing and I cannot experiment with it very easily. That is why we have Jupyter or Google Colab. Is this clear? It depends on you, whether you want to continue with your previous session or you want to reset back to your initial guess and start with that. Okay? Any questions?
I have a question in terms
Yes.
of application more. So like if I keep this value, this is like it is very slow. So
It's very slow, but I did not start with this value. Right? Learning is only during training. We haven't discussed this now. But this hyperparameter is only during training. Once your machine has learned,
yeah.
it knows that value of W is minus 5.
So in application it will just take this.
It will just be this. So your forward pass is the only thing. Forward pass, remember, is your hypothesis. So let's say you come up with a new y, a new x. Give me a new x. 15. let's say. So your forward 15. Okay, you get minus 76.
So
That is
if
your
it's
hypothesis.
the -5 and the +6.
Exactly. Forward is your hypothesis. Now, once you're done, all you need is just the forward function. That's it. This is what gets deployed on the user's machine. And as you can see, it works like that. It doesn't take time. Even if it took you months to arrive at this answer, once you have the answer, it can run like that.
So if the alpha.
It doesn't matter.
But the bx1 doesn't matter.
Once the machine has been trained, the alpha, all the hyperparameters, they don't matter. All the hyperparameters that we've done up until now. Right? There are some hyperparameters which do matter, but over here. Okay? Is this okay? All right. So now what you need to do is, number one, run this. I'll share the notebook with you, but I highly recommend, it's not too much code. Especially if you're going to stay in this area, I highly recommend that you run this once. Okay? And make sure that you understand each line. The second thing is, go back to the slides and look at the slides, the 2 or 3 things, and try to map everything over here. It's exactly the same thing that we're doing. Okay? This thing, this loss, looks like this, and not a bowl, because the bowl was not the loss. The bowl was the derivative of the loss. Okay? So make sure that you keep these things separate. Right? So this is a different plot. This thing is a different plot. The gradient, the J plot was a different plot. Right? So all of these things are different. Okay? So make sure that you can separate them from each other. All right. That's it for today.